Hey everybody, and welcome in. Welcome in. Hopefully I'm coming through all right. Looks like everything's going good on my side. Got the audio mixer. That's looking pretty good as well. Welcome in. Apologies for changing the time on the live stream. I think going forward, what we're going to do is 2200 Pacific Standard Time. Just makes things a little bit easier for me. Gives me a day of rest because I'm typically working 12-hour shifts, and then after work going to the gym, doing a bunch of stuff, and like I just overslept today. So apologies for that. And then I got up and decided to do some gaming with the family, and family comes first. I'm making this YouTube content to just try to help other people get into networking, maybe break it down a little bit easier to understand, bit by bit, piece by piece. And if we get some interaction in the comments while I'm live streaming, we can talk about different discussion points there. So today the agenda is the CompTIA Chapter 4, CompTIA Network Plus Chapter 4. Hello. Hey, nice to see you, Chris Loves Tofu. Welcome back. Welcome back, Chris. Hey, nice to see you. So today we're going over the CompTIA Network Plus Chapter 4, which is the current Ethernet specifications. And I think with this one compared to other stuff, it's a lot less covering concepts with networking, and this one is more along the lines of I appreciate it, Chris. I appreciate it. And it's more along the lines of with this one, we're going to be working on memorization, if you would. So with the I appreciate it, Chris. With the chapter 4, so we have the Ethernet standards. We're going to go over copper, which is our 10 base T, our 100 base TX, 1000 base T, 10G base T, 40G base T. Then we have fiber, which is going to be our 100 base FX. Let me make this bigger. I'm going blind. There we go. That's a lot better. Then our 100 base SX, 1000 base SX, 1000 base LX, 10G base SR, 10G base LR. Then we're going to go over coarse wavelength division multiplexing. That's a mouthful. Dense wavelength division multiplexing, bidirectional wavelength division multiplexing. And I'm a little bit familiar with it. Yeah, chapter 4, let's go. I'm a little bit familiar with it, but one thing I really love about doing the YouTube content versus when I'm doing it in college is I don't have a time constraint. We can go really slow with this. And if we need to break a video down into 2 parts because it takes us a while to work through the content, we'll do that. All right. So I have my Remarkable Paper Pro on the standby. We have our Word document on the standby for our acronyms. That's how we're going to do it going forward. So let me share my desktop with you guys. All right, so over here, we'll just make notes about important concepts. And then on our Word document here, which let's see if I can make that bigger, we're going to be listing down all of our acronyms. So that way, when we're reading through the content, I'm not utilizing acronyms like, let's make sure you guys absolutely know what I'm talking about with CWDM. I won't use CWDM. I'll just use the entire explanation of the acronym. So that way we can reinforce with each repetition what those acronyms stand for. because for me, like I have to hear it consistently in order to remember, oh, CWDM is coarse wavelength division multiplexing. So, and then we'll break down the T's, the TX, the FX, the SX, the LX, the SR, all that good stuff. So chapter 3, if we go back, let me pop that back up real quick. So chapter 3 was our networking connectors and wiring standards. So over here we talked about the different categories of wires, and then we briefly touched on fiber, and then we talked about the different type of connectors for those. This one, we're going over the Ethernet specifications. And let me make this smaller. There we go. And it's just our next chapter in the series. So I don't know if you're able to catch up on chapter 3 there, Chris. I did post the live stream video. And we're working on consolidating those into shorter form videos that take out a lot of the pauses and all of the unnecessary research that we did for fun. All right. So let's just get moving. And we'll keep this up here. We'll just keep this up here. Until I'm told that, hey, you have a copyright strike, I'll just work through it with you guys. I don't know how that all works out. We'll play the risky biscuits for you guys. All right. So we had our introduction there. So let's just start working our way down. I'm just going to read through it, maybe skip through some stuff here and there, but that way you guys have full exposure to the chapter itself. It's all good, man. It's all good. All right. So before we dive into the complex worlds of networking devices, the TCP, IP, and DoD models. So TCP is the Transportation Control Protocol. IP is the Internet Protocol. DoD is Department of Defense. What we're talking about here is like DoD actually is what was doing the research into making networking a thing. So that's why the DoD models were important. IP addressing, subnetting, and routing in the upcoming chapters, you have to understand the big picture of LANs, local area networks, and learn the answer to these key questions. How is Ethernet used in today's network? What are media access control addresses? And how are these identifiers utilized in networking? So over here, we'll just start with our stuff, which is we have TCP, which is our transmission control protocol. And then we have IP, which is our internet protocol. We have MAC, which is media access control. All right. We have LAN, which is, hopefully everybody has that one down right now, local area network. All right. Let's start moving our way down. This chapter will answer those questions and more. I'll not only discuss the basics of Ethernet and the way MAC addresses are used on Ethernet LAN, on an Ethernet LAN, I'll also cover the protocols used with Ethernet at the data link layer. So remember, the data link layer was our layer 2 of the OSI, or Open Systems Interconnection model. You'll also learn about the various Ethernet specifications. So now let's get started with the fundamentals of connecting two hosts together. All right, so our networking basics. Networks and networking have grown exponentially over the last 20 years. Understandably so, they have to evolve at light speed just to keep up with huge increases in basic mission critical user needs, ranging from sharing data and printers to more advanced demands like video conferencing. Unless everyone who needs to share network resources is located in the same office area, an increasingly uncommon situation, the challenge is to connect the sometimes large number of relevant networks together so all users can share the network's wealth. Let's take a look at how communication happens on a basic local area network, a LAN, which I started to discuss in Chapter 1, Introduction to Networking. Starting with Figure 4.1, you get a picture of a basic LAN network that's connected together using an Ethernet connection to a hub. Remember the dumb hub? Yes. This network is actually one collision domain and one broadcast domain. But don't stress if you have no idea what that means. I'll start to cover those terms in this chapter. However, I'm going to talk about both collision and broadcast domains in depth in Chapter 5. So our next chapter will get more in depth, and we'll briefly cover that today using Cisco Packet Tracer. So we have two hosts, and then we have a hub, and that's this figure. So let's go, just for fun, and set that up in Cisco Packet Tracer, which, remember, is a free thing you can get online. I'll post the link in the comments so that way you guys can get set up. All you have to do is register with an email address, and it's completely free. All right, so if we're going to set up the network to look just like the figure he has here, we're going to have two host machines. So we'll grab two PCs, PC1 and then PC2. And then we're going to grab a hub. So networking devices, and then we're going to go to hubs, and we're going to grab a hub. So hubs, if we recall from one of my videos, they're dumb. They work on the physical layer. And all they're going to do is they're going to receive information and then shoot it out across everything else in the network segment. So we're going to then connect our machines up to the hub through their Ethernet ports. And you can see our hub has a multitude of Ethernet ports here. Same thing through our Ethernet port into the hub. So now we have our two computers configured. All right. And as I had mentioned in my What is a Network video, we have our two friends and we have a way for them to talk. So just in like real life, when you want to talk to your friend, you have a few methods of doing so. You can either call them, talk in person, text them, email them. There's a means of having two friends talk. Well, here we're using Ethernet and we're using a hub. So once we have our friends set up, we're going to give them names. Is a hub a bridge? Not quite, no. Bridges can be a little bit smarter, meaning they will actually look at a MAC address, if I recall correctly. Okay, so an access point is a different thing. Like you have your wireless access points. For example, if you're in a business, that's its own thing, but they kind of work in the same principle as a hub, which they definitely cover in one of the chapters a little bit later once they start talking about access points. But a hub is just a way of interconnecting a multitude of hosts. And our hosts are like our computers, our printers, our servers. It just allows us to interconnect a bunch of things together, and it has no intelligence. It does not assess any data. It just receives data and then splits it out into everything on its hubs. So hubs aren't like switches. Switches assess the MAC address and will forward the traffic intended for the recipient. Hubs are dumb. They'll just broadcast it all. And I'll show you an example. So let's get our friends all set up. We're going to go into the desktop IP configuration, and we're just going to give them some names, 192.168.1.1. We'll get a default subnet mask in there. Don't stress about that too much. And then we're going to go into our second friend, desktop IP configuration, 192.168.1.2. And just the demo why a hub sucks, we'll go ahead and get a third device set up. And we'll wire you up to the hub and wire that one up. And then we'll go desktop IP configuration 192.168.1.3. I'm just assigning them random IP addresses, right? Okay, so we have three friends and we want them to talk. So we'll just grab data and put it in friend 1, and we want to talk to friend 3. All right. And we see that we're successful. But what does that look like? What does that look like? Well, let's see what that looks like. And we'll hit play. We'll see the data goes to the hub, and then watch what the hub does. It sends it to everybody. The hub will send it back to everybody. And then we get a reply message from the hub, from our friend, like, hey, yeah, that message was for me. Here's my response. And the hub again sends it out to everybody on the network segment. So that's why they call hubs dumb, because they don't assess any of the data in the packets. They receive data and they'll forward it off to everybody on the network segment. So ARP, Address Resolution Protocol, is a bit different. ARP is used more so that a node can figure out who's on its network segment or figure out where another node is located. So a hub being spray and pray. Yeah, exactly. That's exactly a good way of putting a hub, spray and pray. Yeah. Hey. So like I attributed a hub a lot like, oh no, you're good. You're good. I attribute a hub to a lot like mom and dad are sitting outside on the back porch, and we have our 3 kids out, playing in the backyard. So we have our first node, which is mom, and then dad's the hub. Mom tells dad, hey, can you have Jimmy come in and wash his hands? Dad is the hub. So dad screams, Jimmy, come in and wash your hands. And it's up to each kid, Susie, Jimmy, and Bobby, to figure out if that message was meant for them. Then Jimmy sends his reply of, okay, on the way. And then dad looks at mom, Jimmy's on the way. And then it's up to mom and everybody else to figure out if that message was for them. So that's the way I see it. All right, so let's go ahead and get rid of friend number 3, and then we'll get back to the content. Exactly. I'm not Jimmy. All right. So figure 4.1, which we just covered, which is, well, I could have used Bob and Sally. They had examples for me already. Okay, about figure 4.1. How would you say the PC named Bob communicates with the PC named Sally? Well, they're both on the same LAN, local area network, connected with a multi-port repeater, So the ports are just the slots on the back of the hub to where you can plug in. And Cisco Packet Tracer will show us that if we click on the hub. Let me hit escape. So we can see the back of the hub. These are each ports where you can plug an Ethernet wire into. I'm sure that's kind of small, but we can hit zoom in. Yeah, there we go. These are each ports. A multi-port repeater just repeats the messages. So, well, they're both on the same LAN connected with a multi-port repeater, a hub. So does Bob just send out a data message, hey, Sally, you there? Or does Bob use Sally's IP address to put things more like, hey, 192.168.0.2, are you there? I hope you picked the IP address option, but even if you did, the news is still bad. Both answers are wrong. Why? Because Bob is actually going to use Sally's MAC address known as the hardware address, which is burned right into the network card of Sally's PC to get a hold of her. So the network interface card, the NIC card, is on your computer or whatever node you have. And that's where the Ethernet plugs into. So when you plug your computer up or you plug your PC up, here, I got a crappy laptop to use as an example. There we go. So we'll make my camera big. So right here, where the Ethernet cable plugs into, that is your network interface card, right? So when this goes and connects to your motherboard, this network interface card has the burned in MAC address, the media access control for your device. Plug that back in. All right. This is all good, but how does Bob get Sally's MAC address when Bob only knows Sally's name and doesn't even have her IP address? Bob is going to start by using name resolution. Hey, we were talking about that, weren't we? Host name to IP address resolution, something that's usually accomplished using domain name service. And note, if these two hosts are on the same LAN, local area network, Bob can just broadcast to Sally asking for the information. No DNS needed. Welcome to Microsoft Windows. Here's the output from a network analyzer depicting a simple name resolution process from Bob to Sally. So we have the time, we have the source, that's the source MAC address, the destination MAC address, and then with that, IP address. That's our IP address, and then our destination IP address. Protocol is NBNS, name query, NB Sally. As already mentioned, because the two hosts are on a local area network, Windows Bob will broadcast to resolve the name Sally. Notice destination 192.168.0.255 is a broadcast address. Let's take a look at the second part of the information. So that's one thing that's worth jotting down in our note. Let's see. Are you showing up? Yes. Is when, I'll write bigger. When an IP address ends in 255, it is a broadcast address. All right, so when an IP address ends in 255, it is a broadcast address. So that's why you would never name your computer 192.168.1.255, because for that network, the 192.168.1, if that's how you set it up with your subnet mask, if that's your network, if you ended it in 255, it's going to broadcast to everything on there. So take note of when I was setting up my computers, I have 192.168.1.1, which we can write a note for that. So we have 192.168.1.1 over here, and then over here we have 192.168.1.2. So we have two different computers. And just for the sake of this, let's just say that this is the network, 192.168.1. And we'll make a note of that. So our network is 192.168.1.x. So this is our network we have set up here. So we have our network of 192.168.1.x, and you can see how our computers fall in line with that, right? They're part of the network, and then they have the number that represents the computer, .1, .2. We can't use .255 because that is the broadcast address. So when .255 is used, that's what sends a message to everybody on that network. So that's already pre-programmed. It's a thing that computers understand and computers will do. So we can't assign that value to a computer on our network. All right, so let's get back into it. So let's just refresh what we just read there, okay? Here's the output from a network analyzer depicting a simple name resolution process from Bob to Sally. We have our time, we have our source IP address, we have our destination IP address, and then protocol information associated with it. I'm not too familiar with what type of tool he's using for his network analyzer. I have Wireshark, but I have a lot to learn before I can read that. Yep, 255 is my screaming IP address. All right, everything that ends in .255 is for broadcast. So 255 equals screaming. Just remember that. All right. As I had already mentioned, because the two hosts are on a local LAN, local area network, Windows Bob will broadcast to resolve the name Sally. So we know Sally's name. Notice the destination address 192.168.0.255. So that's the destination. You see how we sent it to 255? So that way we would broadcast to everybody on the network segment. Okay? It's a broadcast address. Let's look at the second part of the information. We have Ethernet 2. We have our source, SRC is source. So we'll put that down. SRC is source. Is Sally's name the MAC address? Oh, Sally's name the MAC address. So we'll get into that in a little bit when it comes back. We'll probably, yeah, let's get into that in a little bit. I don't want to throw out a wrong answer. I'm sure they'll cover it in just a second. So we have SRC, which is source. Then we have DST, which is destination. And then, so with a broadcast, it can be something that ends in 255, or it can be all Fs. All Fs. I'm not sure what you wrote there, Chris Loves Tofu. I can kind of read Japanese, but not a lot. All right. So this output shows that Bob knows his own MAC address, which that's interesting. If they're going to call that a MAC address, that's okay. Okay, there we go. This is the MAC address right here. This is Bob's MAC address. So we have our source IP address, and then we have our MAC address. And then destination broadcast, this is what we're going to use to broadcast at the MAC address level. All Fs. So, another note. When, let's create some space. When broadcasting, with MAC address, it is, what is it, 8 octets of Fs? Where'd you go? 1, 2, 3, 4, 5, 6. 6 octets of Fs. So it is F, 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 F. Oh, we don't need the parentheses. That's just more to show everything. So F, and then colon, FF, colon, FF, colon, FF, until we get to the end. All right. This output shows that Bob knows his own MAC address and source IP address, but he does not know Sally's IP address or MAC address. So Bob sends a data link layer broadcast of all Fs and a plain IP LAN broadcast to 192.168.0.255. So it ends in that 255. So the important parts to pick up here is our broadcast can be all Fs and it can end with an IP address of .255. You're going to learn all about broadcasts in Chapter 6, Introduction to Internet Protocol. After the name is resolved, the next thing Bob has to do is broadcast on the LAN, local area network, to get Sally's MAC address so he can communicate to her PC. So we have our time, our source, broadcast, and then we see our protocol information, ARP, Address Resolution Protocol, who has 192.168.0.3 tell 192.168.0.2. So this is what we're doing with an address resolution protocol. Who has this, and tell this person who that is. All right. So we'll check out Sally's response next. We have our time. The source will be Sally. The destination will be Bob. Address resolution protocol, ARP. 192.168.0.3 is, here's my MAC address of Sally. Then we have time, source, which is Sally, destination, which is Bob, NBNS, name query response, NB, 192.168.0.3. So let's see if he gets into the acronym NBNS, which I think is like name broadcast something. I'm not seeing it yet, so we're going to hit up the Googles and find out because I want to nerd out on it. Google. Let's see. What is NBNS? Yeah, we'll just say protocol. NetBIOS name service, a legacy networking protocol, part of the NetBIOS over TCP/IP suite that resolves computer names to IP addresses on local area networks. So we'll put that down in there. NBNS, which is our NetBIOS name service. All right, cool. Collecting up the information. So our NetBIOS name service, name query response, NetBIOS 192.168.0.3. So if we go back over this, we have the time of Sally's response, the source, which is Sally, the destination, which is Bob, address resolution protocol, 192.168.0.3. So I'm telling them this is my IP address, and my MAC address is the 000B DB99D35E. Okay, sweet. Bob now has both Sally's IP address and her MAC address. That's her MAC address. These are both listed in the source address at this point because this information was sent from Sally back to Bob. So, finally, Bob has all the goods he needs to communicate with Sally. And just so you know, I'm also going to tell you about address resolution protocol, which we need to add to our list. ARP. Address resolution protocol. And show you exactly how Sally's IP address was resolved to a MAC address a little later in Chapter 6. Importantly, I want you to understand that Sally still has to go through the same resolution process to communicate back to Bob. Sounds crazy, huh? Consider this a welcome to IPv4 and basic networking with Windows. And we haven't even talked about a router yet. All right, good place to pause. All right, so going back over it from the start, the way it works is Bob knows Sally's name. He knows Sally's name, but he doesn't know her details. So Bob sends a broadcast over the network to get Sally's details of, hey, my name's Bob. This is my IP address, and I want to know who has this IP address. And then we have our source IP address, our destination IP address with the 255 for our broadcast. And it's name query for Sally. We know Sally's name. All right. And then we have Ethernet to our source with our MAC address, and then our broadcast of all Fs. And then we have our time, source, our broadcast, and our ARP. ARP, address resolution protocol, who has this IP address? Tell me my IP address. Yeah, we just know Sally's computer name. We know Sally's computer name, and we know she's potentially on our network, but we don't know her IP address or her MAC address. So that's why we send out something on the network with the broadcast address ending in 255, and then we also send out the broadcast of all Fs. Next, Sally's response is, hey, this is the time. Time syncing is important. This is me, my source, and I'm responding to Bob, his source IP address. Address resolution protocol, this is me, and this is my MAC address right here. And then the next part of that is our time. This is Sally again, response to Bob, net BIOS name service, name query response, net BIOS 192.168.0.3. I think that's just some follow-on stuff after that. Yeah, no problem, man. So does DHCP handle that conversion from common name to IP then MAC? No, DHCP, as far as I understand right now, is a little bit different in that it's dynamic host configuration protocol. Essentially speaking, what DHCP is going to do is dynamically assign IP addresses. For example, when you set up your router at home and then you want to connect like your smart TVs, your cell phones, your smart refrigerator, your security cameras, DHCP is going to be what assigns the IP addresses to all of those information of things that are connecting to your network, because you don't want the individual devices trying to create their own IPv4 addresses. So the way they set up the internet is there's a lot of IP addresses that cannot be assigned, and you can access the web with them. I have on my router that goes out to the internet, it has a unique IP address that can reach out to the internet, and that represents my whole network. However, inside of my network, all of the things that are connected to the router are dynamically assigned IP addresses. Exactly. Well, that and IPv4 addresses, there's only, 4.8 billion of them. And if you think about how many smart TVs are out there, how many phones are out there, how many computers are out there, we wouldn't have enough IP addresses. So what they do is they create what's called subnetting, which is we have these IP addresses that are never assigned to be used out in the internet world. They're designed to be used inside of networks like the 192.168.x.x. So yeah, those are reserved IP ranges. And what DHCP does is it dynamically assigns IP addresses to things connecting on the network. So one, you don't have to go in there and statically assign them, meaning I type in every IP address on everything I plug into my network. Like how bad would that be is if you connected your TV to the internet and then you had to go and figure out what IP address you wanted to do. So DHCP helps out with that, as far as I understand, which we'll definitely get into DHCP. I think it's in chapter 6, but slow and steady. All right, we'll move on to the next thing, the Ethernet basics. Time for Monster. One sec. Ethernet basics. Ethernet is a contention media access method that allows all hosts on a network to share the same bandwidth of a link. Ethernet is popular because it's readily scalable, meaning that it's comparatively easy to integrate new technologies such as fast Ethernet and gigabit Ethernet into an existing network infrastructure. It's also relatively simple to implement in the first place, and with it, troubleshooting is reasonably straightforward. Yeah, it is. Yeah, it is tedious. All right. Ethernet uses both data link and physical layer specifications. And this part of the chapter will give you both the data link layer and physical layer information you need to effectively implement, troubleshoot, and maintain an Ethernet network. In the following sections, I'll cover some basic terms used in networking with Ethernet technologies. Let's start with collision domain. So the term collision domain is an Ethernet term that refers to a particular network scenario wherein one device sends a packet on a network segment and thereby forces every other device on the same physical network segment to pay attention to it. This is bad because if two devices on one physical segment transmit at the same time, a collision event, a simulation where each device's digital signals interfere with one another on the wire, occurs and forces the devices to retransmit later. Collisions have a dramatically negative effect on network performance, so they're definitely something we want to avoid. The situation I just described is typically found in a hub environment where each host segment connects to a hub that represents only one collision domain and one broadcast domain. This begs the question, what is a broadcast domain? So going through, drop packets is no bueno. We want to have information go through quickly and work for us. So the collision domain, it is an area where there's a potential for two packets to collide. So I have multiple things attached to a hub, as we saw earlier. Let's go back to Cisco packet tracer and see if I can't make some problems for our network. So let's add some computers for funsies, right? And then we'll have a little testy test for you guys too, just for fun. We'll add some computers. I don't know if we can force it into having an issue or not, but we're gonna look and see if we can. Maybe Cisco packet tracer's smarter than I give it credit for. Because also, just as a prelude into what's in the future, our computers are actually smart enough to figure out if a collision has happened. 4. I think we're on 4. Oh, no, we're on 3. 1.3. And then we're going to desktop IP configuration. All I'm doing, okay, so since we talked about DHCP, so see in my IP configuration, we can select to have DHCP enabled, which allows a DHCP server to dynamically assign us our IP addresses. But right now, I'm statically assigning them. I'm assigning them by hand. And the default subnet mask, let's not worry about that yet. We definitely will cover that later. 192.168.1.5. All right, let's see if we can create some problems. I'm just wondering if we can. We're going to see some chaos, but I don't know if it's going to necessarily equate to problems. So we're going to drop some info. We're going to drop some info. We're going to drop some info. Yeah, let's just drop info everywhere. Let's just wait for the chaos. Everybody's sending data. Well, why can't you send data? Something wrong with you? 1.5. Shouldn't you be 1.2? Yeah. Okay. Well, let's drop some more info. You look like you need to send some info. Oh, I don't think it's going to let me overload everybody. We can only send info one at a time. All right, let's see what happens. We're just going to send it all out. All right. I think we accomplished what I wanted. Yeah, let's see if we can back that up. Let's see if we can back that up. So we see that all of this is coming to the hub all at once. We see we got some issues going on. And then we see that we have another broadcast coming out. This is probably something coming out saying like, hey, everybody, slow it down. One of you transmit at a time, potentially speaking. And then we see we have our third one sending its data. But we've, in essence, created a collision. Because now we're flooding the hub, which doesn't look at anything, with information. And the hub's like, ah! But we can see how we're having some issues potentially lining up with our data packets colliding with one another. And that's one of the issues with hubs, is they're not smart. They can't process the data in any way that is meaningful enough to prevent collisions, like a switch. So that's why they're called the dumb hub, because it creates a collision domain, a place where collisions of data can take place. Like, as this guy is sending a data segment here, this guy could have already sent something and is now being broadcasted to everybody. And on the wire itself, the signals will interfere with each other. And then we'll run into a problem. So if we go back to real time, did we have any failures? Yes, we did. If we look down here at the bottom of my screen, you see how some of our packets failed to reach their destination. We have 2 successful deliveries of information, but we have a lot of failed. All right, so let's just try this with only 2 bits of data. We're going to have 1.1 send to 1.2, and then we're going to have 1.4 send to 1.3. And let's see what this looks like. So we have 2 packets breach the hub. We have an issue, it looks like. The hub's trying to figure out who to send what to at what time. Then we have an issue when we send our packet out. And we have both of them fail. We have both of them fail. So very interesting, very interesting. Anyways, that's kind of like what we're talking about with a collision domain. So next is our broadcast domain. So broadcast domain. Here's that answer. A broadcast domain refers to the set of all devices on a network segment that hear all the broadcasts sent on that segment. Even though a broadcast domain is typically a boundary delimited by physical media like switches and repeaters, it can also reference a logical division of network segments where all hosts can reach each other via a data link hardware address broadcast. That's the basic story, but rest assured, I'll be diving deeper into the collision and broadcast domains a bit later in Chapter 5. So, essentially speaking, let's retouch back on that. A broadcast domain refers to a set of all devices on a network segment that hear all the broadcasts sent on that segment. So let's set up two different broadcast domains. Where's Cisco? There you are. So we got our dumb hub, and then let's go and grab another dumb hub. Boom. How many ports we got? We got 6. We got 5 computers on there. Good. So then wire the dumb hub to the... Nope, that's not what I want to do. We're going to grab a switch. I'll just grab any switch. That's fine. We're going to grab a switch. We're going to Ethernet to the switch. And then we're going to grab switch to the dumb hub. All right. And then from the dumb hub, we're just going to grab 2 computers. I don't think we need to do all 5. We're just doing this for science. All right, so we have 192.168.1.1 through 1.5. So we'll go over here. We'll configure you to 192.168.1.6. And then we'll configure you to 192.168.1.7. So let's see what happens when we drop data from here to here. Let's see what happens. And we'll play the scenario. Should broadcast across all of its ports. The switch will probably trying to figure out who that message go to, sends it off somewhere else, because it has to learn where MAC addresses are located. So we got our reply. Reply gets sent back out. Switch to figure out, hey, none of those MAC addresses lie on my segment. I don't need to send that out. Switch once again blocked it. You see how the switch blocked it? The switch, after it got that initial data and it sent everything out onto the network segments, as it's received information on what MAC addresses are, it'll make decisions on whether or not to send that out to everybody or not. So what we have here is we have a broadcast domain and we have a broadcast domain. The switch separates the two broadcast domains in essence because it'll start reviewing the MAC addresses for that. And that's why switches are always better, because it just stops you from having a flood of garbage on your network. And then let's delete. If we were to send this over here instead, if the switch has learned where all of the MAC addresses are, it should forward that. This computer is like, oh, that wasn't for me. Of course, we're going to send it to the dumb hub. The dumb hub's going to scream it at everybody. Ah! As you see right there. Then we have the reply that's going to come back. The hub's going to scream it at everybody again. Switch is going to be like, all right, well, I know that this MAC address is over here. So let's send that over there. The hub's going to scream it again. And good to go. So you see how it kind of breaks up those broadcast domains? Perfect. All right. So now that I think the switch has learned, so it's probably not going to, but we'll do this as an example to see if the switch has learned yet. The hub is still going to spurt it out everywhere. I don't remember if Cisco Packet Tracer, if I delete the scenario, if the switch forgets everything or not. Okay, so yeah, you see how the switch is like, oh, that's not over here. It breaks up those broadcast domains. So it did remember the MAC addresses and it broke it up. And then vice versa, if we were to create a broadcast here with our hub, the switch should stop it from going over to the other side. So we'll pause, delete that, and then we'll do that example here. And we'll hit play. The hub is going to scream it out to everybody, and the switch should block it from coming over here because the switch has learned these MAC addresses. Or I'm wrong. We'll see. We'll see. Okay, yeah, the switch is blocking that one because it's like, oh, that's not over here. Hub screams the reply. Switch should block it. Yeah. Yeah, that's the thing, though. The switches have to learn the MAC addresses. And you can, I believe switches are configured to, over a period of time, they forget the MAC addresses and then they reconfirm. I think it's like every 30 seconds or a minute, they force themselves to forget where each device is. So that way, if you've installed a new device, the switch will figure out where that new device is, which port it's located on. Okay, that's enough experimenting. Let's get back to the good stuff. Where we at? We're here. We'll minimize you. Okay. So that's about it for our broadcast domain. So we're going on to our carrier sense and collision detection. Carrier sense multiple access with collision detection. And that's going to be our CSMA/CD, which is our carrier sense multiple access with collision detection. All right, CSMA/CD. Ethernet networking uses carrier sense multiple access with collision detection, a media access control contention method that helps devices share the bandwidth evenly without having two devices transmit at the same time on the network medium. Carrier sense multiple access with collision detection was created to overcome the problem of those collisions that occur when packets are transmitted simultaneously from different hosts. And trust me, a good collision management is crucial because when a host transmits on a carrier sense multiple access with collision detection network, all the other hosts on the network receive and examine that transmission. Only bridges, switches, and routers, but not hubs, can effectively prevent a transmission from propagating throughout the entire network. So how does the carrier sense multiple access with collision detection protocol work? Let's start by looking at figure 4.2, where a collision has occurred in the network. When a host wants to transmit over the network, it first checks for the presence of a digital signal on the wire. If all is clear, meaning that no other host is transmitting, the host will then proceed with its transmission. But it doesn't stop there. The transmitting host constantly monitors the wire to make sure no other host begin transmitting. If the host detects another signal on the wire, it sends out an extended jam signal that causes all hosts on the segment to stop sending data. Think busy signal. The hosts respond to that jam signal by waiting a while before attempting to transmit again. back-off algorithms presented by the clocks counting down on either side of the jammed devices determine when the colliding stations can retransmit. If a collision keeps occurring after 15 tries, the hosts attempting to transmit will then time out. Pretty clean. When a collision occurs on an Ethernet LAN, the following things happen. First, a jam signal informs all devices that a collision occurred. Second, the collision invokes a random back-off algorithm. Third, each device on the Ethernet segment stops transmitting for a short time until the timer expires. Fourth, all hosts have equal priority to transmit after the timers have expired. Okay, and this is our example that they're providing us. So we have hosts A, B, C, and D. So A and D start transmitting, and we can see that a collision occurs around C. So what will happen then is we have the jam signal that occurs because of a collision. The collision invokes a random back-off algorithm. Each device on the segment stops transmitting for a short time, and then all hosts have equal priority after the timers expire. So as far as my understanding, the computers will set a randomized period of time, because if each computer waited exactly 10 seconds each and then started retransmitting, we're just going to have the same problem happen again. So we have algorithms in place to create a randomized period of time to wait. And it's not super long. It's not literally like 10 seconds, because if you had to wait 10 whole seconds before your computer started trying to send data again, you would go insane. But we have the collision. Computers observe that the collision takes place. Then we have a jam signal that goes out. Computers pick that up. Oh, there's jam signal. Wait X amount of time, according to whatever my clock tells me. Time's expired. Line's clear. Retransmit. Okay. And the following are the effects of having the carrier sense multiple access with collision detection network that has sustained heavy collisions. There's delay, low throughput, and congestion. Throughput is just the amount of data that can transmit over the network segment. So we have a little note here. Let's check through that. Back off on an 802.3 Ethernet network is the retransmission delay that is enforced when a collision occurs. When a collision occurs, a host will resume transmission after the forced time delay has expired. After this back-off delay period has expired, all stations have equal priority to transmit data. All right. So our next thing seems to be a bit of a different segment. We're going into broadband versus baseband. All right. So this is kind of how we're going to be transmitting data across the medium. So I'm going to go and grab another monster. This one is empty, so give me like 30 seconds. I'll be right back. All right. So we've covered quite a bit so far. Covered quite a bit. Starting at the top and working our way down. We covered some networking basics on what a network would look like with two nodes, two endpoint devices connected to a hub, kind of why hubs suck. Then we covered how they figure out who each other are. Like I can know somebody's name, but I'm not going to know their address, right? It's kind of like knowing your email address versus where you actually live. And then we figured out how we go about resolving that. Then we talked on some Ethernet basics with collision domain, broadcast domain, and then our carrier sense multiple access with collision detection. And we saw that how CSMA CD works. When it detects a collision, it'll send out a jam signal, forcing the computers to wait a specific amount of time that they configure based on algorithms with their clock. Now we're going into broadband versus baseband. All right, let's get back to it, unless there's any questions. And it looks like we're about a fifth of the way done with this chapter. So broadband versus baseband. We have two ways to send analog and digital signals down a wire: broadband and baseband. We hear the term broadband a lot these days because that's pretty much what everyone uses at home. It allows us to have both our analog voice and digital data carried on the same network cable or physical medium. Broadband allows us to send multiple frequencies of different signals down the same wire at the same time, called frequency division multiplexing, and to send both analog and digital signal. Baseband is what all LANs use. This is where all the bandwidth of a physical media is used by only one signal. For example, Ethernet uses only one digital signal at a time, and it requires all the available bandwidth. If multiple signals are sent from different hosts at the same time, we get a collision. Same with wireless, except that uses only analog signaling. And what that looks like, I can draw pictures. And it's something we've covered before, but let's go over here and draw a picture. So let's just imagine this is our baseline, right? Because I'm trying to draw a signal. And what's our signal look like? This is what a signal wave looks like, essentially speaking, except for it goes on and on and on. And what we have here is we have our wavelength. Peak to peak of a wave is our wavelength. And as I discovered, one repetition of our frequency. So the frequency is how often we go from peak to peak. It's just peak to peak over time. That's our frequency. So 1 hertz, like you've heard of gigahertz, megahertz, so on and so forth, just like there's megabytes, gigabytes, terabytes. It's just we're increasing our unit of measurement there. 1 hertz is 1 repetition of our peak to peak, 1 frequency. All right, it's completed 1 frequency, 1 hertz. So that is our wavelength from peak to peak. So with a baseband, we only have 1 type of signal going through the line. And then with our broadband, we can have different signals going through. See how this wavelength in red is different? We can have different frequencies going through the same media with broadband. So the next thing that I think is important to cover is our amplitude, the amplitude of the waves, at least just conceptually. We're not getting into the deep science. So the amplitude of a wave is from here to the top of the peak. So this, in essence, from here to here is our amplitude. And we can do cool things with amplitude. For example, we can have our wavelength. And let's just draw a new example. So we can have our wavelength, and then we can have a wavelength. Oh no, don't do a straight line. That's a crap picture. I'm not the best artist. I'm sorry. So these wavelengths, if you imagine I drew them correctly, are exactly the same. But our amplitude is different. So we'll call this amplitude 1. And we'll call this amplitude 3. And you can represent different information by adjusting the amplitude but keeping the wavelength the same. So for example, this could equal 0 in binary, and this could equal 1 in binary. So we can fluctuate the amplitude to change what we're representing. It could be a 0 or a 1 depending on how we fluctuate it. And then when you run multiple signals of different frequency, remember different frequency is just different wavelength, then you can have more data go through the line at the same time. All right, I think that does it for this picture. Let's go ahead and erase all that. Perfect. So let's get back into it. We'll keep you there. So bit rates versus baud rates. I think I'm pronouncing that correctly. So bit rate is a measure of the number of data bits, zeros and ones, transmitted in 1 second in either a digital or analog signal. A figure of 56,000 bits per second, or BPS, means 56,000 zeros or ones can be transmitted in 1 second, which we typically refer to as BPS. So we can put that there. Lowercase b, not uppercase. BPS equals, BPS equals bits per second. In the 1970s and 1980s, we used the term baud rate a lot, but that was replaced by bits per second because it was more accurate. Baud was a term of measurement named after a French engineer Jean-Maurice Emile Baudot. Did I pronounce that right? We'll see. Because he used it to measure the speed of telegraph transmissions. 1 baud is 1 electronic state change per second. For example, from 0.2 volts to 3 volts, or from binary 0 to 1. However, since a single state change can involve more than a single bit of data, the bits per second unit of measurement has replaced it as a more accurate definition of how much data you're transmitting on one receiver. I think that one is just pretty explanatory, like bit rate versus baud rate. Baud is kind of the archaic, outdated version. Today we're using bit rates, how many zeros and ones we can measure across the line per second. All right, next topic, wavelength. Has anyone ever told you that they were on the same wavelength as you? That means they thought you were basically thinking the same way they were. The same is true of the inverse. If they say, you're not on the same wavelength, with electromagnetic radiation, radio waves, light waves, or even infrared heat waves make characteristic patterns as they travel through space. Some patterns can be the same, and some can be different, as shown in figure 4.3. Each wave pattern has a certain shape and length. The distance between peaks or high points is called wavelength. As I had mentioned, see? Peak to peak, wavelength. So this is a shorter wavelength, this is a longer wavelength. It's literally just the length from peak to peak on a wave. Each wave pattern has a certain shape and length. The distinction between peaks or high points is called wavelength. If two wave patterns are different, we would say they're not the same wavelength. And that is the way we tell different kinds of electromagnetic energy apart. We can use this to our advantage in electronics by sending traffic on different wavelengths at the same time. So we can do that by sending traffic on different wavelengths at the same time. Pop quiz, what is that? Is there anybody watching that can answer? Is that baseband or broadband when we send traffic on different wavelengths at the same time? I'll check and see. Maybe I'm talking to myself. Okay, just me. All right, so that would be our broadband. Broadband is when we send traffic on different wavelengths at the same time. So here's our example of shorter wavelength. Here's our example of longer wavelength. In the following scenarios, I'm going to cover Ethernet in detail at both the data link layer, which is layer 2, and the physical layer, layer 1. Half and full duplex Ethernet. All right. Which we've covered in a video beforehand of simplex, half duplex, and full duplex, but we'll get into that here since it's in the chapter 4. Just so you know, half duplex Ethernet is defined in the original 802.3 Ethernet specification. Basically, when you run half duplex, you're using only one wire pair with a digital signal either transmitting or receiving. So half duplex is either you are transmitting or receiving. This really isn't all that different from full duplex because you can both transmit and receive. You just don't get to do it at the same time running half duplex as you can if you're running full duplex. Here's how it works. If a host hears a digital signal, it uses the carrier sense multiple access collision detection protocol to help prevent collisions and permit retransmitting if a collision occurs. Half duplex Ethernet, typically 10 base T, is only about 30 to 40% efficient because a large 10 base T network will usually provide only 3 megabits per second to 4 megabits per second at most. Although it's true that 100 megabits per second Ethernet can and sometimes does run half duplex, it's not very common to find that happening anymore. In contrast, full duplex Ethernet uses 2 pairs of wires at the same time instead of one measly wire like half duplex employs. Plus, full duplex uses a point-to-point connection between the transmitter of the sending device and the receiver of the receiving device, in most cases, the switch. This means that with full duplex data transfer, you can not only get faster data transfer speeds, but you can get collision prevention too. Sweet. You don't need to worry about collision because now it's like a freeway with multiple lanes instead of a single lane road, provided by half duplex. Full duplex Ethernet is supposed to offer 100% efficiency in both directions. For example, you can get 20 megabits per second with a 10 megabits per second Ethernet running full duplex 200 megabits per second for fast Ethernet, or even 2000 megabits per second for gigabit Ethernet. But this rate is something known as an aggregated rate, which translates as you're supposed to get 100% efficiency. No guarantees in networking as in life. Full duplex Ethernet can be used in many situations. Here are some examples. From a switch to host, from switch to switch, from a host to a host using crossover cable. You can run full duplex with just about any device except a hub. Yeah, hubs are dumb. They're not smart. You may be wondering if it's capable of all that speed, why wouldn't it deliver? Well, when a full duplex Ethernet port is powered on, it first connects to the remote end and then negotiates with the outer end of the fast Ethernet link. This is called an auto-detect mechanism. This mechanism first decides on the exchange capability, which means it checks to see if it can run 10, 100, even 1,000 megabits per second. It then checks to see if it can run full duplex. If it can't, it will run half duplex instead. Hosts usually auto-detect both megabits per second and the duplex type available, the default setting. But you can manually set both the speed and duplex type on the network interface card, as shown in figure 4.4. All right, that was a lot to cover. So essentially, to break down kind of the important part of it, a hub kind of screws you over a bit when it comes to full duplexing. And then we have simplex, which is you can only transmit in one direction. We have half duplex, which is you can transmit in one direction or receive in one direction, but you cannot do both. And then full duplex is I can send and receive data at the same time. Let's see, anything else I missed with that? So with half duplex, you only really need one pair of wires, which is two wires. One pair, two wires with half duplex. With full duplex, you need four wires. One pair of wires is for sending. One pair of wires is for receiving. So two wires you send, two wires receive. You need at least that for full duplex. And then the total amount of data you can transmit over a line is called the aggregated rate, meaning it's what you're supposed to get if it's 100% efficient, but no guarantees. And then when you're firing your computer up, it's going to test and see what type of connection it has, whether it's half or full duplex, and it's going to test the speed in megabits per second that it has. And then here's our little figure that goes over how to go and check link speed and duplex. And then it has the auto negotiation, which is where it goes and figures it out itself, or you can statically assign a value. And like the only thing I can think of as far as like wanting to statically assign a value here is if you wanted to lower the bandwidth of individual nodes over your network, so that way everybody gets a consistent speed together versus one computer has super quickness and like everybody else is struggle busing. So today it's pretty rare to go into a network interface card. That's what NIC is. We'll put that over here just in case So NIC is our network interface card. It's pretty rare to go into a network interface card configuration on a host and change these settings, but this example demonstrates that you can do that if you want. So we have a note here. Remember that half duplex Ethernet shares a collision domain and provides a lower effective throughput than full duplex. So lower effective throughput just means it doesn't transmit as much data. Throughput is just a way of saying how much data is going over a line, like how much work is it doing. Then full duplex, which typically has a private collision domain and a higher effective throughput. Lastly, remember these important points. There's no collision in full duplex mode. A dedicated switch port is required for each full duplex host. The host network card and switch port must be capable of operating in full duplex mode. Now let's take a look at how Ethernet works on the data link layer. All right, and before we get into that, I'm going to take a quick break, text the lady, see what she's up to. All right, so give me a minute or two. Thank you. Everybody.